All right, again, welcome back. We're starting on page 25. We'll take a quick look at the calendar because there's a lot of action happening in the next few classes. So first of all, your test corrections are due as of this moment. Put them in the green folders right now. The original test and the corrections. Got to get both of them in there for me. Let's see, there is a project outstanding. That's the Gamma project. Everybody has the Gamma project as a copy. Right, that's not going to be due until we come back, March 23rd, which is the Monday right after break. There is a take-home quiz that I'm going to give you today at the end of class. You will hand that back in to me on Friday, right? I'll give it to you today, you hand it back Friday. And then on Friday was that unannounced other take-home quiz just on U substitutions. For many of you, this will be cake easy and you'll get through it very quickly. For others of you, it's going to take you more time, and those are the people that need to spend more time on U substitution. So I think it's okay. There's not going to be any time limit on that U substitution quiz. Take it however you want to take it over the break. And it should be something where we get 100. That's the goal. Okay, any questions on the calendar? Yeah. It's just in one more quiz. I'll just add one more. Yes, I'll give it to you today. You'll hand it back to me Friday. After the break. Yes, yeah, the project and the other quiz will be due when we come back after break. Other questions on the calendar? Okay, so then the last thing on the calendar today, we're going to cover our second day about improper integrals, and today we'll see something called the comparison test, which just as a sneak preview, there will be another day on comparison tests. April 22nd, mark your calendars. So we're going to come back to this guy in a little while. Let me also say this. Today's class and parts of this Gamma project are very mathy. Not that the stuff we've been doing has not been mathy to date, but when I say mathy, I mean they're really like theoretical in parts, like very proof-based. And for some of you, this will be the first time that you ever really try to write down like a proof. And I'll give you step-by-step instructions today because we're starting this comparison test today. But I just want to point out that this is going to represent a change for many of you. And so just kind of giving you a heads up that this is not going to be just more calculations. The goal today isn't to say, oh yeah, the area, if we look under this curve forever, is 10. That's something we did last time. But just that the area is finite and we're not going to be able to actually calculate it, but we will prove beyond a shadow of a doubt that it is finite, or that it is infinite, all right? So very, very mathy is what I'm calling it. All right, which also means that as you're working on this project, so in particular, question 5 on the project and question 8 are basically proofs. In fact, that's the word. It says you're gonna give me a proof that something is true. And so again, this will be the first time some of you will be writing proofs. We'll give you practice on it, but it's coming up here in this project. All right, so we're on the top of page 25, and we'll start with our daily summary, Kyle. Okay, so we'll start with a Mathematica demonstration. I think this is the first time I'm showing you Wolfram's CDF player. Have we looked at this before? Yeah, so you guys know Mathematica. It was created by Stephen Wolfram, and this is another thing created by that same company. This is free. Mathematica is not. But people around the world that have Mathematica have made these little demonstrations that you don't need to pay for Mathematica to look at. So we are looking at something that was free. It's like a player for somebody who's already made some Mathematica thing. And there's just under 10,000 of these free demonstrations available online. This is one of them. There's really, really neat stuff there, not just math, but also computers and sciences and all kinds of crazy stuff. So at the moment, we are going to be looking at the graph of 1 over x to the n for different values of n. So I'm just going to move this and you'll see that things change, right? So now let's slow it down just a little bit and figure out what's going on. So I'm going to make n equal to, what am I doing here? Can I make it, oh yeah, I'll just type it in, 2. Okay, so n equals 2 means we are looking at 1 over x squared, yes? And 1 over x squared, you guys saw last time that if we look at this area to the right, underneath 1 over x squared, is that finite or infinite? It was finite. And do you guys remember what the magic power was that was the cutoff where this would be either finite or infinite? was 1 was the magic cutoff. So this is on your packet here. It said that if you integrate 1 over x to the p, then that thing converges when p is greater than 1 and diverges if p is less than or equal to 1. That was going up to infinity. And then as part of the activity yesterday as well, we went from 0 to 1, but 0 to any positive number is really the same result. And you found that the convergence happened in the opposite cases. Converged when p was less than 1 and diverged when p was bigger than or equal to 1. So this is stuff that we did in the activity last time, but I think that this demo here kind of drives it home. So apparently purple means finite and pink means infinite. And at the moment, if we're looking at 1 over x squared, then this stuff to the right is finite and the stuff to the left is infinite. That's what you saw last time. And then as we shift things around, at the moment now, n is about 1.1, so it's 1 over x to the 1.1, still finite, still infinite, but I don't know if you can tell the tide is turning, right? Like here, the purple is smaller, but getting bigger, right? Here, the pink is bigger, but getting smaller. You see that? And then when we're at the magic value of 1, let's see if it'll stop right there. Not quite, so we'll just type it in. So magic value of 1, what did we decide on both sides? It diverged. Both sides were infinite. But then as soon as I cross just to the other side of 1, so 0.985, this part was infinite and this part was finite. And I don't know, I just kind of like the way this thing looks. It's just like there's this like symmetric kind of thing and it's very fluid. And just depending on which side of the magical cutoff of 1 you're on, one side is infinite and the other side is finite. Okay, so let's come back here. So that was our big conclusion from last time. And now we're going to take a look at number 3, which says, suppose that 0 is less than or equal to f of x is less than or equal to g of x for x sufficiently large. So here's an example. F is this x to the negative 3, which is 1 over x cubed. And then g is 1 over what? X squared. Okay, so there's f and there's g. And it says, for what values of x is this thing true, that f is less than or equal to g? When is the dark blue less than or equal to the light pink? From what number? From 1, isn't it? Right? Like the blue is underneath until we get there, and then all of a sudden the blue is above, yes? Okay, so we've got this condition that as long as x is sufficiently large, in this case bigger than 1, then the blue is underneath the purple, yeah? Okay, but if I think about this graph, integral of 1 over x squared dx from 1 to infinity, this is our big conclusion. Is this finite or infinite? Remember, it's determined solely based on that number. That number is bigger than 1, therefore this is finite. We saw that last time. So I don't actually care what it is. I'm just going to write finite. You could find the exact answer, but finite is all I'm after. And what that means is that the area underneath the purple, if we go forever, is finite, yes? So now I'm going to draw in blue, or I'm going to write in blue, integral from 1 to infinity of 1 over x cubed, right? That's the blue curve. And again, I don't care what this area is, but what can you say about the area of the blue if we go forever? Finite or infinite? It's also finite. Because? It's always below, right? We know that the purple area is some finite number, and the blue area is less. Less than finite is still finite, right? And again, don't care about what the numbers are. All we care about is it finite or is it infinite? And so then our conclusion here has to be that this is also finite. And so what we just applied here is something called the comparison test. If you have an integral going forever and you know the total area is some finite number, and then you have another function which is what compared to the original function? Which is below it, which is less, then the area underneath that smaller function must also be finite. Okay, so this is what we're concluding here for number 4. If we know that the integral of g, which was the bigger one, if we know that that guy converges, finite, then what can we conclude? That the integral from a to infinity of f of x converges. It's finite. What's that? So I'm not trying to pin down exactly what the limiting area is, but I can say that if the purple area is finite and blue is definitely smaller than that finite area, then blue has to be finite as well. Yeah, this is what we saw last class, and it was a surprise, is that you can actually go forever, but still have the area be some finite number. Yeah, well, you should believe it because you did it last class. Okay, other direction now. Suppose that we know that the integral forever, the forever area of the lower curve, that's the F curve. We're going to fill this blank in. There's another direction to this comparison test. What would be useful to us if the smaller area was what kind of a thing, finite or infinite? Was it if it were infinite, right? Because if the smaller area is infinite, then what can you say about the bigger area? It's got to be bigger, and it's therefore got to be infinite. We buy that? If yeah, we've got to have f less than g forever in order to apply these things. So suppose that you know that the integral of the smaller one diverges, meaning the area is infinite, then we conclude that the integral of the other guy, the bigger one, finite or infinite, got to be infinite. It has to be bigger than the infinity that we already saw. So this one also diverges. Ryan, can you read that last sentence for us? Okay, thank you. Let's go to the next page. Number 5, Brendan. Thank you. Isaac? Thank you. Number 6, we're going to use our comparison test to make one more big conclusion, and it's about this integral from 1 over e to the ax, where a is some number. Okay, so suppose for 1 second that a is -3. Just making up a number. Then this integral is really 1 over e to the -3x. Some number to infinity, which is really just e to the 3x, right? So we could do a substitution to actually find it, but all we care about today is it finite or is it infinite? We don't actually care about doing any integrals. Think about the graph of that, and then think about the area under that graph. Is it finite or infinite? Infinite. And it's like infinite quick, right? I mean, like this, like the curve itself is getting huge, let alone the area which we're allowing to go forever to the right. So this one clearly diverges. So can you guys tell me what about A that I chose made it so this one definitely is infinite? It was a negative, right? Any negative power really means this E is on the top, and therefore it's going to blow up. So it diverges as long as A is less than 0. Yeah, so what if A is equal to 0? Is that what you were asking? Yeah, so what if, so give me a number. -0.5? What about that one? Is that, what did you say? Yeah. So that graph is still an e to the x kind of graph, right? It's not going to grow as quickly, but it still blows up. Okay, so if A is 0, then that's 1 over 1, which is our horizontal line at 1. Is that area finite or infinite? Infinite. So converges or diverges when A is 0? Diverges. Okay, so let's add the 0 to this guy. Okay, and now we got to fill in the other blank. Now, I mean, if we're right, if we're dead on, then the other blank is A greater than 0, but we have to convince ourselves that that works. So suppose that we just make up our favorite number that's positive in this case, like 7. And so now I'm thinking about the integral of 1 over e to the 7x. Yeah, so thinking about 1 over e to the 7x, that's an exponential decay function, and it's going to get very close to the x-axis very quickly, but that doesn't mean the area is finite. Just because we get close to the x-axis doesn't mean the area is finite. But how does this guy compare to the function like 1 over x squared, for example? Yeah, which one gets to the x-axis faster? E, right? E beats just about anything you can name. So what inequality goes between, greater or less? Less. The first guy is definitely smaller than the second guy. We buy it? And what do we know about this integral of 1 over x squared? Is it finite or is it infinite? It's finite, because that squared is bigger than 1. So if that guy's finite, then what about the first guy? It's got to be finite, and that's our comparison test. And I picked 7. What do we think about picking like a decimal, like 0.5? Or 0.7, how about that? Which one wins? Which one gets to the x-axis faster? It's still the e to the 0.7x. I mean, it might take a little longer. I mean, the x squared might look like it's winning for a little while, but we know e is going to beat x squared eventually, right? And so any number that's positive, any a that's positive, will still have the same conclusion. So then now I'm feeling pretty good that we can fill that blank in with an a bigger than 0. Yep. So let's go back to our, no, the greater than is only on this side. Yeah, just greater than for that blank. Let's bring it back here. Okay, so all right, so for example, 0.8, or how about 0.5? What we discovered last class was even though this curve is getting to the x-axis, yes, it still has infinite area there. It just doesn't get to the x-axis fast enough to make it finite. So this area is infinite. And again, if you let it go forever, it gets bigger, 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 and it has no maximum, no upper bound. The area in here is, no, you guys proved this last class, didn't you? Okay, yes, I buy it that it's hard to wrap our head around this kind of stuff. We're playing with infinities, and people that thought about infinities 100 years ago went to the crazy house. I mean, like honestly, like mathematicians went insane thinking about this before we really had other people saying, hey, it's okay to think about infinity. It doesn't tend hard enough. That's a good way to think about it. Yeah, no. Right, so here's what we did last class. We started with this 1 over x squared from 1 to infinity. It sure feels like this has to be an infinite area in green because you're going forever to the right and it's always positive and you just keep piling more positive stuff on. So it felt like it should be infinity. The surprise is that it's finite. So you shouldn't be surprised that anything going forever is infinite. You should be surprised that anything going forever might actually be finite. And what we discovered after we changed that troubling infinity to a b was that this was the area if we just cut it off at some arbitrary b value, which is minus 1 over b plus 1. And then we sent b to infinity and we said, hey, this part really just tends to nothing, and so the whole area must tend to 1. And we actually plugged in some values of b, like if b is 100, then it's negative 100th plus 1, 0.99. So if you go from 1 to 100, the area there is 0.99. And if we went out to 1,000, it was 0.999. And it's yes. So that's the surprise, is that anything there could be finite. Well, what you guys did in the activity was played around with the numbers near the cutoff. So do you guys remember, or can you just look up real quick? The 1.1, was this guy finite or infinite? You proved that this one was finite last time. You actually found, yeah, because this power is more than 1, it turns out. It's finite. I think you guys found that the answer here was 10, right? The area of this thing was 10. And then you tried this guy, and all of a sudden ln made an appearance, and ln of something infinite is infinite. And so even though these curves, 1 over x to the 1.1 and 1 over x, look almost identical, and they both look like that, just that subtle difference going from a power of 1.1 to a power of 1 takes something that was finite and makes it infinite. And then over here, this guy was even more infinite, if that makes sense. And that was going from 1 to infinity. And then on the next page, you looked between 0 and 1, and here the problem isn't going to infinity, the problem is going to 0, because these curves all have this vertical asymptote at 0, right? Can't divide by 0. And in this case, you found that this area right here was infinite in here. This one was also infinite, but then somehow, miraculously, when it got to 0.9, it became finite. And so you wrote down some conclusion down here, which we have summarized right in here, is that 1 over x to the p, from a number to infinity, the magic cutoff is a power of 1. If you're on the good side of 1, you converge. If you're on the bad side of 1, you diverge. Yeah. Good. Okay. So let's just, okay. So then I will say this. We now have 3 tools that I'm expecting we're going to make plenty of use of in today's class. Here are 2 of them. 2 of the tools are right in here. If you see any of these, any function that looks like either of these, you get to use this thing and hope that a comparison test works. And then the third tool is this guy that we just found here with 1 over e to the something. So these are 3 facts that we can just bring to the table to any of these problems. So let's try number 3. It says determine convergence or divergence for these integrals. So 1 over e to the x plus 1. Honestly, I don't know how to find an antiderivative of this, so I couldn't have done this problem in the last section. I don't know. I mean, you could change the infinity to a b, but I don't know how to find an antiderivative of 1 over e to the x plus 1. So I can't actually tell you like that the answer is 7 or 10 or anything. What? Did you find one, Levi? No? All right. What's that? We'll type it into Wolfram Alpha. Okay, but what we're going to do is we're going to compare this guy to something that we know the behavior of. And what we just discovered is that we know 1 over e to the anything. We've got it figured out. So basically, we're going to ignore this plus 1 here, because if I ignore the plus 1, then I can use this former result. So here's what we're going to do. We're going to try to compare e to the x plus 1 to e to the x. We're going to put some inequality in between. What goes in between, less or greater? Greater, yeah? So now I'm building the fraction parts. And now it changes directions. This will be a pretty common technique for us. When you put 1 overs, the inequality goes the other direction. And then the other piece that we're going to bring in here is that the integral of 1 over e to the x, just that guy without the plus 1, going from 1 to infinity. Looking at our big result in number 6, does this converge or diverge? How much is a? Is 1, which is bigger than 0. So this guy converges since a equals 1, which is greater than 0. And this is us starting to write mathematical proofs, and we're going to be writing a lot more words than maybe we're used to in a math class. The sentences don't have to be very long, they just have to capture the key ideas. You got to say, hey, Ian, I know we're just referencing number 6. The value of a in this case is 1, it's bigger than 0, so that thing converges. Can we finish this one and then we'll answer that question? Okay, so let's ask ourselves if the inequalities go in the right direction, because if it's not, we won't be able to do the comparison. The function we're interested in is smaller than the one that we know about, yes? And the one that we know about is finite. So what about the original one? Must also be finite. And what's that called? It is convergent. And what's the name of the test? The comparison test. That's what we just used. So we'll just write out our final sentence here. So by the comparison test, that's what I want you to write, by the comparison test. Okay, so our first proof. They're not all that painful. Like I said, it's just a little different than maybe you're expecting in a math class. But you've gotten pretty high in terms of math, and at some point math goes from calculations to proofs. So right here, we're just kind of doing a little bit of proofs as an intro type thing. Notice that I have no idea what it converges to. Like I don't know if it's equal to 10 or 100 or 0.004, but that's not the goal. The goal is either finite or infinite, that's it. Well, yeah, if it diverges, then it goes to infinity, so there's nothing more to do. But converges, I'm saying that we can't do what we did last class, which was say what it converges to. Okay, so I think Alex was asking a question before that I wanted to put off until now. What if this were going the wrong way? Then we couldn't do it. Maybe another one to compare it to, but it's worth pointing out, if that inequality isn't going exactly the way you need it to go, comparison test does not apply, right? If you know this is finite and this is bigger, well, something bigger than finite could be finite, but it could also be infinite. And so that's why we don't get any information if the inequality goes the wrong way. Alex, was that the question you were asking before? Okay, let's try part B. Oh yeah, Kevin. You were saying that yes. Yes, 5 and 8 will be structured like this. Yes. Are you asking about the first line we wrote here? Yeah, you can just go to that. Sure. Okay, part B. Got to figure out what that behaves like. X is going to infinity, so anything other than leading terms is pretty much irrelevant, right? If X is huge, then what's the thing that dominates on the bottom? Is the X to the fourth, right? And adding 4 times something huge is nothing compared to the huge thing to the fourth. So what we're going to do is we're going to compare this guy. Sorry, we're going to compare this guy to just the leading term. Okay. Ignoring everything except the leading term. Which direction does this go in the inequality? That is greater, yes. X's are all positive, right? We're out near infinity, so that's greater. So then if I put an x squared, well, I don't know, we can do it in 2 steps or 1. Up to you guys. We'll just do it in 1. This is what we're doing, is we're using the comparison test to ignore the 4x plus 1. Okay, so I did 2 things in 1. First, we did a 1 over. What happens to the inequality when you do a 1 over? It switches. And then I multiplied both sides by that x squared term, and that doesn't change the inequality, right? This reduces to 1 over x squared. Finally, we're at an integral that we're going to be able to use. The whole idea of this comparison test is that you got to use stuff that you know, and at the moment we know 3 things. And if it doesn't look like one of those 3 things, we can't do it. Okay, so this integral right here, this is the one that we need to figure out whether it converges or diverges. This is one of our important ones. Converges because p is greater than 1. This one had a p in it, the other one had an a in it. Doesn't make a difference, but at least we're using the letters that are in the notes there. This guy converges since, how much is p? 2 and the magic cutoff is 1. Right? That was on the previous page. And I want to point out that the cutoff for the x to the p is a different cutoff from the e to the a. Right? Here the magic number for this p business is 1, but just up above, what was the magic cutoff? 0. You just got to keep them straight. Question? The comparison wouldn't be valid, because if you compare it to 1 over x to the 4th, here, so we'll write it here. I'll just copy this and then I'll erase it. But this guy right here, x to the 4 plus 4x plus 1, compared to 1 over x to the 4th, I think that 1 over x to the 4th is smaller. Yeah, and this guy goes the wrong way, right? So the thing we want is bigger than finite. Yeah, it doesn't help me. But at the moment, the thing that we want is smaller than what kind of a thing? A convergent integral. So what about the thing we want? Also converges, so we're just going to write that same sentence by the what? Comparison test. We're going to start abbreviating CT. By the comparison test, and then we're just copying the original thing. What does it do? Also converges. That's what we did. Okay, let's try part C. Part C. Integral 2 to infinity of 1 over the cube root of x squared minus 1. Which part of that is probably irrelevant? Is that minus 1? Agree? All right, x is huge. Subtracting 1 is going to make little difference. So how about we kind of ignore it? So cube root of x squared minus 1 is the original. I'm going to compare that to the cube root of x squared. What symbol goes in between? Less, right? Because you're subtracting 1. So that first guy is smaller. So then my next step is putting 1 over each of them. Inequality this time flips because we did the 1 over. What doesn't do anything? Well, let's see what the integral of the thing that we have here does. 2 to infinity. This is one of our useful or important conclusions. Does that integral converge or diverge? Is this on this page or on the previous page? This is on the previous page. It's 1 over x to what power? To the 2/3. 1 over x to the 2/3, does it converge or diverge? That diverges. So this guy right here diverges. Since is the letter A or P? This is P. Since P is equal to what number? 2/3, which is smaller than the magic cutoff of 1. So Levi's gut reaction was that the inequality is going in the wrong direction, because in the first two, we needed our thing to be smaller. But in this case, the thing that we're interested in is greater than what? Infinity, right? So what can you say about the thing we're interested in? It is also infinity, which is our conclusion. By the comparison test, the original thing, what does it do? Diverges. I like putting the word also there just so that I can just kind of keys into the fact that it's the behavior of the one that's known that is copied by the unknown one. Yeah, CT is now our abbreviation for comparison test. Okay, welcome to the wonderful world of proofs. The activity starts on the next page. Remember, the goal here is to get good at this new skill of writing proofs. So if the answer to every one of these is either converges or diverges, that is far less important to me than writing out the steps in the proof, okay? Cooper. Okay.
I think comparing this to like identity proofs is